Today I want to start talking about graphs of polytopes. And I should tell you right away that there is very, very much to say about this, and I'm only going to scratch the surface, because I want to just discuss a couple of things. If you want to go in depth into this topic, then you're very welcome to, and this is another possibly good topic for the project. And if you guys want more pointers on this, I'm happy to send you some papers or books, things like this. One way of starting this discussion is by talking about what we said at the beginning of last class, which is that if you're in this doesn't really mean anything, but in R4 or higher, in more than four or more dimensions, we see a new phenomenon that we didn't have in 2 or 3 dimensions. We have a new phenomenon which is that you can have different polytopes that have the same graph. Okay. And it's even more dramatic than this, because actually we can have lots of polytopes for which the graph is the complete graph, and they're not just the silly polytope. They're not just simplices. They're more interesting polytopes. So, let me say polytopes which are not the simplex. Whose graph is the complete graph. Okay. And so what I want to do today is to begin to discuss some generalities about graphs of polytopes. Okay, so what is this graph? So we have a polytope P, and I'm going to define the graph G of P. And it's a pair of 2 sets. The vertex set of the graph is the vertices of P. And the edge set of the graph is the edge set of P. In other words, you know that the polytope has faces in every dimension between -1 and full dimension. What we're going to do is just pay attention to dimension 0 and dimension 1. We only care about the vertices and the edges. Okay? So this we're going to call the graph of P. But then we're going to think of, when I say graph here, I mean graph in the sense of graph theory, in the sense of combinatorics, where we no longer care about the metric properties of how this thing is sitting in space. We only care about the incidences between the vertices and the edges. Okay? So for example, the graph of the 3-dimensional cube, well, one way of drawing it is like this. And I'm drawing it kind of curvy so you realize that it's not about distances or anything. All we care is what are the vertices, what's the set of vertices, and which vertices are connected to which. Okay? And so that's the graph of the 3-dimensional cube, right? It's kind of a funny looking 3-dimensional cube, but I precisely want to make that point that it's not a metric picture. Okay? Okay, so let me make a definition. I'm going to say that a linear function c dot x on R to the d is said to be in general position with respect to a polytope P in d dimensions if basically it should take different values on all the vertices of the polytope. So I want to say that C vi is different from C vj for any vertices vi and vj of P. Okay? So again, let's consider the three-dimensional cube in R3, and let me give you three functions, and you're going to tell me if they are generic or not, if they are in general position or not. So one function could be x. Another function can be x plus 3y plus 9z. And another function can be x plus y plus z. Okay? So, for example, this one, the first one, x, is that in general position with respect to the cube? So I see that you guys are nodding, so why not? So nodding is no or yes? I always forget. Nodding is, and nodding is what? Yes. So you're not nodding, you're shaking your head. Thank you. So you're shaking your head. So why are you shaking your head? So this is not generic because, for example, the points, well, the vertices 1 comma anything have the same value of that function. Okay. What about x plus 3y plus 9z? Well, you have to kind of try it, and if you try it and if you plug in the 9 vertices, you're going to see that you get 9 different things. Okay. And what about x plus y plus z? No, because, for example, 1, 0, 0 and 0, 0, 1 have the same value. Okay. Now, if you think about this graphically, so here's the cube. I said this is no. So let's say that the axes are like this. X, y, and z. Then it kind of makes sense that the function x, which is pointing parallel to the axis, you should not be calling it general because it has the same direction as the edges of the cube. Okay? Or for example, x plus y plus z is kind of pointing in this direction, and you see that these 2 points that we're saying are level, they have the same value, are this one, and also this one has the same value. Okay, and the point is that this function, if you think of it as a vector, it's orthogonal to this plane, so it's not general. But somehow the way that you should think about this is that if you just point in any random direction, then you're not going to be so unlucky as to get the same value at 2 of these vertices. Okay? To put it precisely, in almost any direction. Almost any direction is general. And when I say almost any, I mean a set of measure 1 or probability 1, if you know what these things mean. Okay? So almost everything is general, basically. Okay? Now, if I have a linear functional that is general, such a linear functional is going to induce an orientation of the graph. And when I say an orientation of the graph, I mean that I'm going to take each edge and I'm going to say it either points to one direction or points to another direction. So I'm going to assign an arrow to it. And what I'm going to do is I'm going to say that the edge from Vi to Vj is going to be directed from the smaller to the larger vertex according to this linear function. Okay? So if c dot vi is less than c dot vj for an edge, then I point it in this direction. If c dot vi is bigger than c dot vj, then I point in the other direction. And if c dot vi equals c dot vj, then that means that I'm not in general position, so I don't consider that kind of c. Okay? So I get an orientation of g of p, which we call the orientation induced by c. Okay? And what I want to do now is prove a couple of things about this orientation. Maybe let's just go over here and state it over here. Proposition. The orientation of the graph of a polytope induced by a generic C. When I say that C is generic, I mean that it's in general position with respect to P. Satisfies the following properties. One, it's acyclic. Okay? And what I mean is that what this means is that you don't have a directed cycle that you can follow on the graph. Okay? So maybe we'll draw a picture. This means no directed cycle like this. Okay. And has a unique sink. And when I say a sink in a graph, I mean a vertex such that every edge is coming in and no edges are coming out. Okay? So what I mean by this is a vertex with no outgoing edges. Okay, so it's a vertex such that all the edges are coming in. And let's call this sink S. Okay, so this is S. So then I want to say that the point S is the unique point in the polytope where the linear function is maximized. Okay, the linear function c dot x is maximized precisely at that point. Okay. that make sense? Any questions about it? About the statement? What do you think? Yeah, I agree. It does. What do you think that source? So the question was, does it also have a unique source? And presumably, kind of by symmetry, the answer should be yes. And presumably, that source should have another property, which is what? That it should be where that linear function is minimized. That's true. So let's. By the way, is this obvious to you? So let me draw a picture, and I'm hoping that staring at this long enough, you'll see that actually it's kind of an obvious statement. It shouldn't necessarily be obvious right away, but maybe if I draw a picture, it's a little bit clearer. So let's take some polytope. Is that a polytope? It's a polytope, yeah. So when I say that I'm choosing an orientation. I'm choosing a generic C. Basically, I want to choose some direction for which no bad things happen. So I don't know. Let's say something like this, maybe. Okay. So then what I'm doing is basically I'm orienting all the edges according to that direction, right? So it's kind of like this, like this, like this. Here, for example, it's kind of a close call, but you see that according to this direction, this vertex is further than this one. So like this, like this, like this, like this. It looks kind of like that, okay? The way that I'm getting those directions is, for example, saying, look at this edge, okay? So I have to say, according to the linear function, which one of these vertices is farther in this direction. And you can just pictorially see that this vertex is farther than this vertex according to this direction. Mathematically, what that means is that the dot product of this vertex with this direction is bigger than the dot product of this vertex with that direction. So I'm basically orienting all the edges according to how things flow in that direction. And so that basically means that the graph is all kind of flowing in that direction. It's like water is flowing through the graph, and it really flows in that direction. And so that means that there shouldn't be cycles because everything is kind of flowing in the same direction. And there should be a unique sink because, well, we'll see why. Give me just a second. So,
alternatively, could you construct a bounding hyperplane perpendicular to that line segment, and then look at the distance from each vertex to that hyperplane?
Sure. Yeah, that works too. That's a very good point. What if I had an edge like this? Then would this one be farther or this one be farther? Well, if there's a tie, that means that my linear function is not generic. Okay? That's a very good point. So that's why every edge is oriented unambiguously, and then you see that everything is kind of flowing in that direction. And I mean, it kind of makes physical sense that if everything is flowing in one direction, then it must be blocked somewhere because it's a finite thing. That's a sink. Okay? Why can you not have more than one sink? Because if you had two sinks, they would have to have the same value. That's kind of the idea. So this is the picture you should have in mind, that you're kind of letting the polytope flow in that direction. Okay? So in particular here, the sink is... So there better not be two sinks where I did something wrong. So this one is not a sink because this one is coming out. And this one is the only sink. Okay? So that's the idea. And the proof is not too different from the idea. We're gonna do it. So, well, we have 3 statements here, so maybe let me call them A, B, and C. Okay. There should also be a unique source, which is this one. Okay, so we need to prove that this graph is acyclic. In other words, that there's no directed cycle. Well, let's assume that it has a cycle and get a contradiction. So if I had a cycle, let's say from V1 to V2 to V3 dot to Vk back to V1, it's a cycle, then what happens? Well, if the edge is directed from V1 to V2, that means that C dot V1 is less than C dot V2. If the edge is directed from V2 to V3, that means that C dot V2 is less than C dot V3, so on. So C dot V1 is less than C dot V2, less than C dot V3, so on, less than C dot Vk. But if the edge is directed from Vk to V1, then this is less than C dot V1. Okay? And so we got C dot V1 less than C dot V1, a contradiction. Okay. So that's why I can't have a cycle. B, there is a unique sink S. So that's actually 2 statements. 1, that there is a sink, and 2, that it's unique. So first, let's show there is a sink. Okay. So what am I going to do? Start at a vertex. Okay, pick a vertex. And then kind of go with the flow. And somehow, if you keep going with the flow, there's only one place that you could end up, which is a sink. That's basically going to be my argument. Okay? And well, that's the kind of argument that sometimes you see it in a class, but then if you try to write that in the homework, then you get points off. So, so let's actually write an argument of how would you actually say that? Okay, I'm going to say pick a vertex V. Either it's a sink or it's not a sink. If it's a sink, then I'm done, right? Because I just want to prove for now that there is a sink. If sink, done. If not sink, what does it mean not to be a sink? It means that you have outgoing edges. So consider an edge from V. Maybe let's call it V1. Okay. Consider an edge from there is an edge from V1 to something, and I'm going to call that V2. Okay? And then I'm going to say, okay, either V2 is a sink or it's not. Right? So if V2 is a sink, then I'm done. But if it's not, then I can consider an outgoing edge from V2 to somewhere. And I can call this vertex V3. And I should point out that this V3 is different from V1. Why is that? Because you would have a cycle. Okay? And then I continue. If V3 is a sink, then I'm done. If not, then consider an edge from V3 to V4. And again, because there's no cycles, that means that this V4 cannot be V1 or V2 or V3. And then I would say, well, this is a finite graph, so this cannot go on forever. Right? So at some point, this process must end, and when it ends, I have a sink. So because my graph is finite, this process ends at, and the only way that it could end is at a sink. Okay. So that's why I know that there is a sink. Okay. Okay. So now let's prove that that this sink is actually unique. So let's consider some sink. So okay, so sink is unique. Consider a sink. Let's call it T. Okay. So here's T. Okay. And we know that all the edges of T are incoming. Okay. And let's give names to the neighbors. Let the neighbors of T be, let's set n of T equals V1 up to Vk. Okay. So these are the neighbors of T in the graph. Okay. They are the edges, they are the vertices V such that Vt is an edge. Okay. And then I'm going to say the following. One thing that you should realize, well, so let's maybe draw the rest of the polytope. We don't know exactly what it looks like, but it might look something like this. Okay. Look at what happens if you stand at T and look at the cone generated at T. So we're going to stand at T and then look at the cone generated by these rays. Okay. And let's call this cone, let's see, what did I call it here? I guess I didn't call it anything. So let's consider this cone. I'm going to call it C. Maybe C sub T. And it's basically going to be, I stand at T, and then I look at the cone of all these vectors, V1 minus T, V2 minus T, up to Vk minus T. Okay. Is that clear what I'm doing? Consider the cone starting there. And what can you tell me about that cone? Contains P. Right? How would you prove that? One way of proving it is that if you remember this business about vertex figures, you'll see that if you look at the vertex figure of T, what's the vertex figure? It's the little shape that gets formed around here. And basically the cone is just taking the vertex figure and just kind of sending it out. Okay? And we already talked about how the faces of the vertex figure correspond to the faces of the polytope that contain T. And what that means is that the rays of this cone correspond to the vertices of the vertex figure, In other words, and I mean, you can see it very easily in this picture, there is a bijection between these VIs and the vertices of the vertex figure. Vertices of the vertex figure, which we call P mod T. Okay. And what's the bijection? Well, each one of these rays contains one VI, and it contains one vertex of the vertex figure. And this statement basically follows from this. So this implies this. And this again is a little detail that you can fill in. Okay. But I think it's intuitively clear, and the key ingredient of the proof is this observation.
The vertex figure is full dimensional, right?
The vertex figure, remember, is one dimension lower because it's the result of taking my polytope and slicing it with a hyperplane. So if my polytope has d dimensions, the vertex figure has d minus 1 dimensions.
It doesn't seem like the rays that we're creating here off of T, though. How do we know that we're encompassing a much higher dimensional polytope? We're working down here pretty flat dimensions.
So is your question why do we know that this cone C sub T has the same dimension as P?
Yeah, I don't know a lot of intuition about dimension 25, and I'm not sure that my representation that I do here, which is just a projection down onto R2, when I make that what we would call a fan of rays, I'm actually going to grab all those other dimensions.
Mm-hmm. Well, so let me tell you one way of saying that CT has the same dimension as P is basically that there is this containment. So if P is full dimensional and CT contains it must be full dimensional. I mean, I agree with you that this picture is helpful, but shouldn't entirely be trusted, and that's why I wrote exercise here. And I mean, by the way, I want to make a comment about this, that I keep putting these little exercises and I keep putting them on the forum, and I'm serious that these are things that if I just do them in front of you, I think it's not very instructive, and what's really instructive is for you to sit down and prove these things. And it's really to build your chops to the homework. And I think you've noticed in the homework there's a lot of things that you want to say, and you don't really know how to say them. And if you go back to all these little exercises that I keep giving you, they're exactly those things. Okay, and I think that's what I want to say about that. So I would really encourage you to work the details out, and I'm happy to talk to you. But these are exactly the little observations that is very important, that you can turn geometric intuition into some algebraic computation. But this is an instance where the picture of the geometric intuition is right, and it does work out. Now, why am I doing all of this? Remember what I'm trying to do? I'm considering a sink T, and I'm trying to prove that it's unique, that there's only one sink. What I'm going to do is I'm going to actually prove C. And C says that the sink is the place where this function is maximized. And that's what I'm going to do. I'm going to consider a sink, and I'm going to prove C. I'm going to prove that this point maximizes C dot x over the polytope. And then that'll prove its uniqueness because there's a unique point that maximizes that function. So I'm going to prove C. How do I prove C? Well, I need to prove that T maximizes C dot x over the polytope. So let me take a point in the polytope and prove the desired inequality, right? So let's take a point P in the polytope. And I need to show that C dot P is less than or equal to C dot T. Then I will have proved that C dot x is maximized at T. Okay. And And that's where this is going to come in useful, because if P is in my polytope P, that means that P is in my cone C sub T, which means that I can write it as T plus a combination of these guys. So let me call it lambda I times Vi minus T from I equals 1 to K, where here I'm considering a cone, and remember that in a cone, the lambda i's have to be greater than or equal to 0, but they don't have to add up to anything in concrete. By the way, this is another comment that I want to make. I have several comments to make because I'm almost finished grading the homework, and I'm seeing some mistakes that you guys have been making. And one is you want to be always very careful about these conditions on these lambda i's. You want to be very careful about the difference between a linear combination, an affine combination, a convex combination, a positive combination. So for example here, because it's a cone, then the lambdas have to be greater than or equal to 0. They don't have to add up to anything. So now let's compute C dot P. So C dot P is equal to C dot all of this, right? So C dot T plus C dot all of this stuff. Okay. And let me distribute this, because I can bring the C dot into the summation. Okay. And also C dot, a constant times Vi minus T, I can take the constant out. Right? So I get lambda I times C dot Vi minus T. Okay. And then let me just distribute this a little bit more. C dot T plus summation from I equals 1 to K of lambda I times C dot Vi minus C dot T. Okay. So I make this computation, and the point of this computation is that you see each one of the edges is directed from Vi towards T. Right? So the edges go from Vi towards T, and what that means is that C dot Vi is less than or equal, is less strictly than C dot T, because C is generic. And so what that means is that this thing is negative. Yeah? This is negative. The lambda i's are greater than or equal to 0. So what I have here is C dot T plus a bunch of negative things. So that means that this is less than or equal to C dot T. Okay. Which shows C. Okay. It shows that T is the point where C dot X is maximized, and therefore it shows that it's unique. And the reason for that is that because C is generic, that means that the function C dot X cannot be maximized at two places, because there would be a tie between those two vertices. Okay. And so that concludes the proof of A, B, and C. Now, I think it's instructive to think. I mean, we started with geometric intuition, then we made a proof out of it, but now let's go back to geometric intuition and let's see what we actually did. You see what I'm saying here is that to know if T is where the function is maximized, all I needed to do was look at the neighbors. Yeah? And if T is bigger than all its neighbors, according to the linear function, then I basically prove that T is bigger than the whole polytope. And that's something useful to think about. If you stand in a vertex of a polytope, then either it is the maximal place or one of its neighbor vertices is higher. Okay, that's a good geometric intuition to keep in mind. And now we have a proof for that. Okay, this is a proof. Okay, so that's this result. And with that, I want to tell you very briefly about one of the most important applications of theory of polytopes of discrete geometry, which is the theory of linear programming. Now, generally, if you're going to learn about linear programming, you're going to learn it in a class that's going to be called optimization or something like this. And I'm going to give you a very simplified version of linear programming. But linear programming is basically the following problem. Maximize, or let me say, given C, A, and B, maximize C dot X subject to AX less than or equal to B. Okay, that's the main goal of linear programming. Maximize C dot X subject to AX less than or equal to B. So if you just look at this from what we've done so far, we understand perfectly well what we're doing here, because we know that when I make X be subject to a system of inequalities, AX less than or equal to B, I'm restricting X to be inside some polytope or polyhedron. Right? I don't know if it's a polytope because I don't know if it's bounded or unbounded. Okay? But this is a polyhedron, and I'm asking to maximize C dot X over the polyhedron. In other words, I'm just asking to find the maximal face. So from our point of view, this is very simple. This is just finding the maximal face in direction C of the polyhedron AX less than or equal to B. Okay. But don't be fooled. Don't think this is trivial, because you should know that. I mean, maybe some of you know already, if you've done linear programming, that this is an extremely, extremely, extremely powerful technique in optimization, and people really do use this every day in practice in real life applications. The point is, and I'll give you one example, but the point is that there's a lot of optimization problems of different kinds that if you just spin them in the right way, they can be rephrased as this, okay? And the point that I want to make with that is that basically, if you want to get really good at linear programming, what you need to get really good at is basically just finding maximal faces of a polyhedron. Okay? You need good algorithms to do this. And so what I want to do now is show you the first intelligent algorithm for linear programming, and it's actually one that is extremely useful. So, and actually I should tell you that very often in linear programming you don't necessarily care about finding the whole face, you just want to know what the maximum value is. And in that case, what you need is just to find some vertex. So either, if you're very ambitious, you can find the maximal face, or if you're less ambitious, you can just find some vertex of it. Okay? And once you have a vertex of the maximal face, then you know what's the maximum value of this function, which is what you might be looking for. Okay? So I want to give you an algorithm and I want to give you an application, and hopefully I have time. So this is called the Simplex Algorithm. It's due to Danzig. It says the following: find a vertex, any vertex V. Well, maybe I should say, yeah, okay, so find a vertex V. Okay, I wish I hadn't erased my picture that I had here. Let me just draw it again real quick. Is that a polytope? Not yet. That's a polytope, right? No. Yeah? Yeah, it's a polytope. So the algorithm says, okay, choose a vertex. It doesn't matter which one. And then you just ask yourself, is it a sink or not according to this orientation? So if it's a sink, then you're done. If it's not a sink, then what you're going to do is just, among all the neighbors, you're going to find one that's higher, and you know that it exists. Okay? So find an edge from V to somebody else. Let's call it W. And repeat. So if you're used to the notation of algorithms, they do this thing which is unsettling to mathematicians, which is to redefine V to be W. So you forget that you had called this V, and now you call this V, and you let that's what you would tell a computer program to do. Okay. Repeat until you're done. Repeat until done. That's it, a very simple idea. So here, this is not a sink, so that means that I can walk forward. This is not a sink, so that means that I can walk forward. And eventually, I'm going to have to hit a sink because there's no other thing that can happen. And then this is going to be the solution to the linear program. Do you have a question?
So then instead of trying to look at all of the faces or all the vertices at once, you're following a path through until you hit a sink.
Exactly. So that's the power of this technique, that it's a very local technique. And that's why it's the first smart algorithm, because it's actually using the fact that we have a polyhedron to say, well, let's just kind of, each step is very local and it's very easy, and you know that eventually it's going to end. Now, like I said, this is very much an oversimplified discussion, because there's a lot of algorithmic issues here, right? How do you find a vertex? How do you efficiently generate this? All of these things. How do you find a higher neighbor efficiently? How many steps does it take? Is this effective? But what I should tell you is that in almost every, what I should tell you is that this simplest algorithm, with little tweaks, with little ideas of how you can make sure that it runs well, is what is used a lot of the times in practice. Okay? It's not quite as crude as what I'm saying here, but you have to be a little bit smarter. But this is really the beginning of linear programming. And it stems from this fairly simple idea. Okay? What time is it? 3? Okay. So then maybe I'll stop there, and we'll start next time by just giving you a quick idea of the kind of combinatorial problems. If you have a combinatorial optimization problem, how do you make it look like this? We'll discuss that next time.